All right. So today, it's going to be a lot of information coming at you. So I highly recommend, so first of all, make sure you're 100% tuned in. And then I would recommend that you watch the video tonight or tomorrow before it all goes, because there's so many details, so much stuff that we're going to make connections and learn new things. That watch the video soon, because lots of important stuff that will fall out of your brain quickly in the next 24 hours, okay? Potentially. All right, so we're talking about convergence and divergence of sequence and series. All day Friday, we worked on convergence of sequences. So today, it's going to be series. So we're going to start talking about the convergence and divergence of series. And so an infinite series converges if the sum is finite, if the sum actually sums up to something. Okay? And that should be a familiar idea. What would that, do you remember what that's kind of like that we've done recently? What was it? Yeah, someone said it right there. Remember we didn't have proper integrals, right? If you had a rate of change function, and you talk about like over the long haul, what's the accumulation over the long haul? So that's kind of like a sum, right? That's kind of like a summing up all the accumulation over the long haul. And so it's kind of the same thing. It's like an infinite series, an infinite sum. And so we're going to now talk about it in terms of series instead of improper integrals. But there's going to be this very strong parallel today's class between all the stuff we learned with improper integrals and with this infinite series. Okay? So here's first example. So just a refresher. Represent the sequence, the series, and the sequence of partial sums using only symbols a third grader would understand. Okay? So you got three things to write out. Write out the sequence, or a representation of the sequence, the series, or representation of the series, and the sequence of partial sums. But write it out so a third grader would understand what you're writing. Go. Practice. Okay, where's Connor? Connor Simpson. Did I call on you Friday? I don't think you did. Okay, cool. Figured out where I'm at. Okay, so tell me about the sequence, Connor. What's the sequence? What was the next one? Okay. How do you do? 12 over 5? Is that the sequence? The list, right? The list. I equals 1. What's the first term? I equals 2. What's the second term? It's the list. Okay? The series. Where's Carter? Carter Hogan. Yeah, tell me. Okay. So yeah, this is the bottom line. We got to know what a sequence is, and we got to know what a series is. We can't do anything else if we don't know those. So let's try Nikita. Is Nikita here? Let's try Gabriel. Ruggeron. Okay, make a note of this. People aren't coming to class. Sean, tell me about the series. Right. A series is where you just take all the lists of the sequence, every single term of the sequence, and you just add them all together. Make one big sum. All right, so if we weren't sure about that, from here on out, we're sure about it. You just take all the terms of the sequence, and you add them together. That's the series. And then we get all these we get the fancy sigma, right, to abbreviate that for us. But this is the concept, right? Okay, sequence of partial sums. Logan.
The
Okay.
39 tenths.
Where did you get 39 tenths?
From adding up the 3/2 and the 12.
I'm going to write it out that way. Is that okay?
Yeah.
All right. Next one.
And then the third term would be 3/2 plus 12 plus 37 tenths. And then
Right. The sequence of partial sums. Now we make a new sequence. Each subsequent terms of the sequence adds one more term of the original sequence, right? So that's the sequence of partial sums. Questions on that? Okay. Does the sequence converge? If so, to what? So now we can look at that, the general term, 3i squared over I squared plus 1, and use our analysis techniques. Will the sequence converge? The original C, it's the sequence C. Scott?
It will converge because the 3i's squared, the plus 1 is basically going to be negligible compared to the I squared values, really large values. So it'll eventually just tend to 3, so like 3i squared over I squared.
Yes.
Will mean nothing when you have really big values.
Right. So this is this thing where we can consider this like a rational function. One polynomial over another. We can compare the degrees of the numerator and denominator when they're the same and things get big. So when it gets big, it's going to essentially be 3i squared over I squared. Like you said, the 1 will just be negligible compared to everything else. So in the end, and I'm gonna then change this. So what does that converge to then? 3, right? So it's going to be just like, like when I gets to be really, really big numbers, we're essentially going to have what? 3. I'll put it in parentheses because it'll never be, no term will ever be 3, but eventually they'll be indistinguishable from 3. So I'm going to write it that way in parentheses like that, 3, 3, 3. So that sequence will eventually become indistinguishable from what? 3, 3, 3, 3, 3. Okay? Does the series converge? So we can do the same thing, right? We can come over here and we can say, all right, we keep adding them up. Eventually, it's just going to be like this. When those terms get big enough, all the terms that we're adding are essentially going to be 3. Putting it in parentheses because it'll always be just a little bit less than 3. But indistinguishable eventually when I gets big enough. Okay, so Walker, does the series converge?
I'd say it diverges.
Because?
It's going to be 3's added constantly.
Right, we're just, so, remember, so, and this is, what is this like? This is a concept we saw, right? What is this kind of like? Yeah. Yeah, so it's like if we have a constant rate of change of 3 or something, then when, yeah, and a delta x of 1, then our little bits of accumulation in the end are just going to be like adding 3 every time for a change in 1. Okay, so yes, so convergent sequence to 3, definitely a divergent series, right? Because and we just end up adding 3 forever. And that's just going to grow and grow and grow. So what about the sequence of partial sums then? What will the sequence of partial sums do? So remember, each term of the sequence of partial sums is the sum from before plus one more of the new one, or one more term. So what's that? Yeah, it diverges, right? So it's just going to get bigger. Each term is going to be 3 bigger than the one before. Like when I gets big, we're just going to keep adding 3, and it's like the sequence of partial sums is like the accumulation of all terms up to the kth term. It's like we're summing up all of them up to a point, and then we sum them all to the next one, and then sum all of them up to the next one. Well, we're just going to, then that limit of that sequence is just going to be infinity because we keep adding 3. Does it make sense? 6 is an example. Okay, another example. So all 4 bullet points for this one, sequence D. So for sequence D now, do all 4 bullet points again. You're free to talk when you're ready. After you've thought about it, always free to talk. What? You're good. Get it? All right, where's Mallory? Mallory here? Make a note. Where's Pinkfei? Lou? Pinkfei, Lou? Seth?
Do you have any answer all four?
Nope. We'll do a couple here. How about the sequence? Tell me what the sequence is like.
Yes, it'll converge to 0 because the
No.
denominator will grow.
Did you do this first bullet point?
Oh, yeah.
Okay.
Sequence term. Sorry. So the first term is 4/3.
4/3.
Yeah, the second term is 4/6.
4/6.
The third term is 4/11. Comma, dot, dot, dot.
Let's do one more. What's the next one?
Where are we? 18?
18. Okay. And then what would the series be?
4/3 plus 4/6 plus 4/11 plus 14.
Series is just where we take all the terms of the sequence and add them up. Okay, how about Christopher, back to you. How about the sequence of partial sums?
Yeah, 4/3.
Okay,
2. 6 over
4/3. And how'd you get 2?
well, let's see here. It was just 8 over 6 plus 4.
You added those two?
Yeah.
Okay, and you get 2? All right. And then how'd you get the next term?
Just common denominator.
But what did you do to get the term?
I just multiplied over 6, multiplied 6 over 9.
You multiplied something to get this term?
Yeah, just to get a common denominator.
But you were doing a common denominator to do what? What are you trying to do?
I was just adding together.
Adding what together?
Adding 4/3, 4/6.
Okay, yeah. So I'm just asking the very basic question. How do you get this next term? 4/3 plus 4/6 plus 4/11. And you got a number for that?
Yeah. That was 156 over 66.
156 over 66? Okay. Etc. Right? So first term is 4/3. Second term, those two added. Third term, the first 3 added. Anyone get the next term?
Oh my gosh, decimal form.
Whatever it is, right? So it's something ugly. So it's those 4 added together would be the next term. How about that?
It's like 2.58 something.
Okay. So how about this sequence? 4 over I squared plus 2. Where's Zach Hansen?
So the sequence, if it converges,
How do you know?
because the denominator gets progressively smaller while the numerator stays constant. So while the denominator gets larger and larger, it converges towards 0.
Okay. All right. So yeah. So we got a really big denominator, and then we can also say this is kind of like what kind of sequence that we learned on Friday. It's like a p sequence, right? And for a p sequence to converge, all we need is p to be
Greater than 1/2.
for the sequence, right? For the sequence, p has to be, remember? Positive, greater than 0. Remember? I to the square root, I to the 1/2. It still gets big. I to the 1/10. It still gets big in the denominator. Okay, so all you need in a p sequence is for that thing to be a positive exponent. So yes, converges, yes, to 0. All right, how about the series? Does the series converge? So what do we have? We have terms. The sequence, the terms are getting closer and closer to 0. And then we're adding all those up. Yeah, so all right, good. So when I gets big enough, our terms of our sequence are going to be indistinguishable from 0. So then eventually we're adding a really small value, or essentially 0 over and over again. Will the series converge? Okay, you're saying yes. How does the sequence of partial sums relate to the infinite series? So if we kept going with this sequence of partial sums, meaning we keep adding one more and taking a new term by adding one more, adding one more, adding one more, adding one more, and looking at that sequence, what is the result? How does that sequence compare to the infinite series? Let's see. Where's Melissa? Melissa here? Anders, right. How does the sequence of partial sums, relate to the series?
Well, eventually it'll just be adding numbers, increasingly approaching 0. So the sequence of partial sums will approach one number, and that's it.
So the sequence of partial sums will approach a number, and how does that number relate to this whole series? Yeah, it would be that, right? So it would be that number. If you added them all together, it would be the same as the limit of the sequence of partial sums. Because the limit of the sequence of partial sums is like you're just keeping, you add one more term each time of the series. So wherever the sequence of partial sum is going, that's the same as the whole sum of the whole series. Okay, so let's, so this summarizes that. Here we go. So the infinite series converges if the sum of the series is a finite value, and the sum is the limit of the sequence of partial sums. That should make sense. If you really understand the sequence of partial sums, you understand that if you take that to the end, you're just essentially talking about the series, the whole sum. That should make sense. That should make sense. Okay, so let's look at that. Let's look at these two that we've talked about so far in GC. Any questions before we go on? Okay, so let's look in GC here. So I have, where's my files? No. There we go. Okay. So here's those two sequences we talked about, C and D in function form. And so I'm going to graph the sequence of partial sums. So for the different values of I, and let's do blue and red so they are more distinct. The blue one will be C, and the red one will be D. So what did we say about C? The sequence of partial sums is going to do what? That first one we looked at? Yeah, we just like keep adding 3 each time. And then with the D sequence, it's like eventually we keep adding essentially 0 each time, right? So there's I equals, oh, jeez. Okay. So the red one is, the blue one is C and the red one is D. What happens when you keep adding 3? You keep adding 3, it just gets big, right? But if eventually you're adding a smaller and smaller and smaller number, then things level off. Yeah. So this is the sequence of partial sums, right? It's the accumulation of the sum of all the terms up to that one. So this is the sum of all the first 10 terms as a y-coordinate. And this is the sum of the first 10 terms as a y-coordinate for C. Yeah.
You asked, like, it wasn't on there, but I was trying to think of, like, what D would actually converge to, and, like, is that what we're going to get to?
Right, yeah, so I did not ask you what D converged to, and that was on purpose, because that's a harder question. But I did set up, for D, I did set up the sequence of partial sums in a table so we could kind of see. All right, so here, this is for D. I'll make it bigger here. Okay, so we got 4/3 for the first term, 2/3 for the second, and then the sequence of partial sums in a column over here, so we keep adding all, like, S sub D of 7 is the sum of the first 7 terms. S sub D of 10 is the sum of the first 10 terms. And if you look here, so here's by 50, we're up to 3.36, at 100, 3.4, 200, 3.42, 250, 3.43. And so it's still getting bigger, but by smaller and smaller amounts, right? So now we're at 3.43. So then I just got impatient and went to 3,000. And so at 3,000, 3.44278. So you see by the time we get to 300 terms, or even, yeah, so even like 100 terms, it's like the 10th place is locked in. We know it's 3.4. And then by the time we get to something like the 300 or 350 term, now the 100th place, so we know it's a 3. But actually it's not, because when we got to 3,000, that's 3.44. So probably the further you go, the more decimal places get locked in, and then we keep adding smaller and smaller amounts and like fine-tuning it, right? Fine-tuning. Okay, so I just went ahead and said, let's call it 3.443. So then let's graph that line and take a look. So there's 3.443. After 3,000 terms of this, our partial sum is about that, 3.443. So these red dots, take enough of them, they're going to get really, really super close to the sum of around 3.443, where that black line is. This sequence C, its series, is just going to keep getting bigger and bigger, right? By 3 each time. Okay, questions on that? Okay, so this leads us to something called the divergence theorem. The divergence theorem lets us conclude quickly that an infinite series diverges if the sequence that series came from has a specific qualifying feature. So the question is, what kinds of sequences are such that we could immediately conclude that the associated series diverges? So what would be true about a sequence that we could just say, not even a question, don't even want to look at the series, it's going to diverge? What do you think? So what is it about a sequence that you could just immediately conclude that series diverges? Yeah. Okay, is that what you're thinking? Yeah, so exactly. The divergence theorem says that the series diverges if the sequence does not converge to 0. If the sequence does something else besides converge to 0, adding up all the terms will never be a finite value. Should make sense, right? If the sequence converges to -3, then what happens in the end, in the series? -3 plus -3 plus -3 plus -3 in the end, forever.
So what about those weird trig functions where the value goes up and down?
Yeah, so exactly. So if same thing, if the sequence is, jumps around, it doesn't converge. If the sequence doesn't converge, the series will not.
Diverge to infinity.
Yeah, it's got it. Yeah, exactly. Okay, so this will always be the first thing to check when analyzing a series. Okay, if the sequence doesn't converge to 0, game over. The series isn't even worth looking at, right? You just know this thing's going to blow up. Doesn't make sense. So super important. Divergence theorem. So in terms of analyzing series, kind of like the divergence theorem is the first thing we want to do. We want to rule out the, make sure that if we have a sequence that doesn't converge to 0, we're done. Series is not going to add up to something finite. Like we saw with what? C, the C sequence, right? Okay, so then let's look at, am I good on the screen? Can I go on? A question, please.
So if it does converge to 0.
Okay, we're going there. Yes, that's the right question. And that's where we're going in the next little while there. Okay, so the next, let's talk about the harmonic series. The harmonic series is this. So we're going to kind of let go of the I and get familiar with using other symbols as well. So the J is just like I. Because we could use I, we could use J, K, P, whatever we want, okay? So I want you to write out what this means so a third grader can understand. What do all those scary symbols mean? But write it out so a third grader would understand. And where's Jared Vargas? Jared here? Tell me. He said 1 over 1 plus 1 over 2 plus 1 over 3. And then how many things do we add up? All of them, right? Yep. 1 over 1 plus 1 over 2 plus 1 over 3 plus all the way on and on and on. So this is a special series called the harmonic series. Okay? So thinking about on Friday, so this series is based on the sequence 1 over j. What kind of sequence is 1 over j? Vivian knows? No, but just what kind of sequence is it before we say converges or not? Yeah. With p equals? Yeah, so it's 1 over j to the 1. So this is a p sequence, right? With p equals 1. And so convergent or not? Does the sequence converge? All p has to be is greater than 0. All p has to be is positive for the sequence to converge. So absolutely, 1 is greater than 0. So yep, we've got a convergence sequence to 0. Okay? So the sequence converges to 0. What about the series? What about the series? Does it converge to a finite value or not? So we saw that if the sequence does not converge to 0, the series diverges. So what about when the sequence does converge to 0? Does the series converge? Let's see. Okay, let's see. So we had an example of one that did, right? What was it? 3 over I squared plus 1? Was that the one we had? 4 over I squared plus 1. We saw that series, or that sequence went to 0, and that sequence converged to 3.443 or whatever. All right, so let's look at this one. So I'm going to take the harmonic series, and I'm going to compare it to this sequence here. All right, so I'm going to just say those are the same. And then 1/2 is the same. But then instead of 1/3 plus 1/4, I'm going to do 1/4 plus 1/4. What does 1/4 plus 1/4 equal? A half, right? And how does a half compare to 1/3 plus 1/4? Is this bigger or smaller than a half? Bigger, right? Because a third is bigger than a fourth. So this right here is greater than 1/2. Okay so far? And then I'm going to take the next 4 terms. So I took, and I'm going to do 4 1/8 together. And that equals to 1/2. And I'm going to compare that to the next 4 terms of the harmonic. Are the next 4 terms of the harmonic 1/5 plus 1/6 plus 1/7 plus 1/8 greater than or less than 1/2? Bigger, right? Bigger. Because all these are bigger than 1/8. I'm going to do it again. I'm going to take the next 8 terms, or I'm going to make a sequence of 8 terms of 1/16 and compare those to the next 8 terms of the harmonic. Bigger or smaller than 1/2? So the next 8 1/16 is equal to 1/2. And this is going to be bigger than 1/2. Will I ever run out of terms? I can always just double the number of terms I grouped before and make 1/2 and the bottom one. And then that same number of terms in the harmonic will be greater than 1/2. You can just keep going like this forever. So what about the harmonic series? So I got 1 plus 1/2 plus something greater than 1/2 plus something greater than 1/2 plus something greater than 1/2. All I have to do is take double the number of terms that I had in the last group, and that sum will be greater than 1/2. And I'll never run out. I can always do that because I have an infinite number of terms to grab. So the harmonic series does what? Do you see that it diverges? Because it's like it's bigger than just adding 1/2 over and over again. I can always get a group of terms to be bigger than 1/2 by just doubling the number doubling the number in the group that I took before. Uh-oh. So what happened? The sequence does what? The sequence converges to 0, but this series diverges. Okay, so again, this should feel familiar. What is this like that we've done before? Remember what we did? Well, we'll see in a second. So, conclusion. If the sequence converges to 0, what about the series? It has a chance. That's all we can say. It has a chance. But it still might diverge, like the harmonic series. The sequence definitely goes to 0. Those terms will get essentially equal to 0 and indistinguishable from 0. But it still adds up to an infinite value. It still just gets bigger and bigger and bigger. So this goes to, I forgot your name. What was your name? Yeah. Carmen's question, right? Carmen's question was, so if the sequence doesn't go to 0 and we say the series diverges, then what if the sequence does go to 0? Does the series converge? Maybe. Some do, some don't. So these are the interesting ones that we want to look at. That's why we want to look at the divergence test first. If the sequence doesn't go to 0, forget about the series. Not even worth, chiseling at. But if we've got one whose sequence goes to 0, then it's worth analyzing. Some of those series get, whirl off and get huge. Some of those series converge to a value. Okay, so let's talk about p-series in general. 1 over j to the p. Recall that the p sequence converges. This is the sequence now, right? This is the sequence that converges for all p greater than 0. The p series we just looked at, that's p equals 1. So the p series is basically the series made out of a p sequence. Okay? Take a p sequence, make it into a series, we call that the p series. All right? So the p series of p equals 1 harmonic diverges. So the real question is here, for what values of p does the p series converge? P sequence converges for all positive p. We already have an example of one where the series diverges. P equals 1 diverges. So for what values of P does the P series converge? And what would you guess, based on what we've seen before? Greater than 1. I mean, and so this is just like, and we're going to map it out here. This is just very analogous to our improper integral when we did the improper integrals of what, 1 over x to the p. We were doing like p functions, right? We were doing improper integrals of p functions, which is very similar to a series. So if we were to look at, say this is f, so if I have any, so that's like a p function, right? We looked at these. What about the, what should I do? I'll do it here. What about this improper integral, 1 over 1 to infinity of 1 over x to the p? What do we say about that? Divergent or convergent improper integral? That's the one we said will, you know, if your rate of change is this with a p greater than 1, we'll get an amount of accumulation that's finite, right? It'll level off if p is greater than 1. That's what we saw before. So what I'm going to do here is, let's turn this into a series, kind of. So let's look at the whole numbers. And so geometrically, what does that represent? At the rate of 1 over x, if we integrate the rate of 1 over x to the p, which is the height of this function, then integrating from 1 to infinity geometrically is what? Who remembers what that is?
Area under that.
It's going to be the area under that curve, right? At the rate 1 over, at the y value is the rate. So this improper integral will give us all this red area like this. But if I make rectangles, then we'll see that the areas of these rectangles are values of the p sequence. Why? Because the coordinates of this point are 2, 1 over 2 to the p. And the coordinates of this point are 3, 1 over 3 to the p. So this area right here is 1 times area of base times the height, which is 1 over 2 to the p. So that area right there is the second term of the sequence. And this area right here is the third term of the sequence. And the fourth term. So all I need to do is add this 1 right here. This is 1 by 1. Right? This is 1, 1. So if we do 1 plus the improper integral, which is all that area under that curve, what? That's going to be bigger than the sum of, well, we got the 1. It's going to be bigger than the sum of all the black rectangles, right? And that first rectangle, the area, what's that area? 1 times 1 over 2 to the p. Well, that's just 1 over 2 to the p. And what's that area right there? 1 times 1 over 3 to the p. And then 1 times 1 over 4 to the p. And so what is that right there? So can we use summation notation to write out what that is? Well, it's this, right? It's just j equals 1 to infinity of 1 over j to the p. And how does it compare to the red area under the curve plus the 1? It's less, right? So we know this converges. That's finite. what we learned before, right? Improper integral, 1 over x to the p, where p is greater than 1. That's bigger than this whole series. So if you have something that's less than a finite value, it has to be finite as well. So for p greater than 1, that sum converges, because it's like adding up the areas of those rectangles, which are all fall underneath. They're all less, all those areas added up are less than an area we know is finite. So for what values of p does the p series converge? Greater than 1. And we already showed that it diverges for 1. So what about when it's less than 1? Divergent, because you're going to have a bigger number. When p is less than 1, your series will be bigger, and we know that it diverges when it's 1. So it's just like the p series is just like our improper integral, right? We know that improper integral converged when p was greater than 1. So the series, being like a discrete version of that improper integral, also converges. Questions on that? Okay, so geometric series. We talked about geometric sequence, right? So geometric series is of this form. You see that and you think what? Is Noah Dietrich here? Not here. Julia, see that? Think what? No, when you see those symbols, what does it represent? What do you think when you see that?
The sum of all the values from j equals 1 to j equals infinity of AR.
And can you tell me what those are?
So the first one will be a r to the 0.
Okay, a r to the 0.
The second will be a r to the 0 plus.
So is it comma then?
No, it's well, it's comma and then.
So a r to the 0 comma.
Right. And then a r to the 0 plus a r to the 1 comma. Oh wait, no, it's all pluses.
All pluses.
Yeah.
Working it out. That's okay. That's great. So it's all pluses. A r to the 0 then.
Plus a r to the 1 plus a r to the 0.
There you go. Got it. Just had to talk it out. That's okay. A plus a r to the 1, a r squared, a r cubed, a r 4. So you see that thing? You think immediately. You think this. This is what it means. Okay. So what we want to know is, for what value of r does the geometric series converge? For what value of r did the geometric sequence converge? Do you remember that? That was Friday. When did the geometric sequence converge? So we looked at it without the a, but that just multiplying by a doesn't really affect anything in terms of convergence or not. So do you remember, when does the geometric sequence converge? When r is what? Yeah, Jerome? Between negative 1 and 1 is when it converges to 0, right? The sequence. So we want to know, when does the geometric series converge? And I don't have time to do it. Trying to get back to that turtle going across your backyard. It's taking me a long time to get there. So we're going to have to do it on Wednesday. But we'll start Wednesday with this question. For what values of r does geometric series converge? There's a little proof.